All right, everyone, we are going to do a little recap of this friction lab. If you remember the setup here, we had our wooden block, we had our dual range force sensor, and we were pulling the block along. We were taking down some data based upon how hard we were pulling and putting those in the data table and looking at some results of that. So let's take a look here at what the data table looks like. And I'm just going to make up some numbers here to put some numbers in. So what were we doing here? Well, we were putting the wooden block, say for example, on a table to start. And then we were looking for what the peak static friction force was. And if you remember on your logger pro graph, you had a graph of time on this axis and then force on this axis. And then as you were pulling the force sensor, you were pulling, it was kind of going up, 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 and then it peaked out somewhere, and then it kind of went flat like this. And maybe it wasn't exactly like this, but it was something pretty close. And what we were saying is that during this whole time right here that you're pulling, the block wasn't moving. So this was static. And then this part over here was kinetic. And this little spot right at the top there was going to be your peak static friction force. Remembering that static friction is a little bit smart, so when things aren't moving, you can pull and static friction is going to sort of adjust how hard it pushes back in the opposite direction. And as soon as you get it moving, then you run into the realm of kinetic friction. So for your peak static friction, you were picking this number right there, and then your mean kinetic friction, remember mean means average, was kind of like the average of this whole area over here. I had mentioned in class, and maybe on a video as well, that kinetic friction was always the same. And that's true, but in the lab, real world's a little bit different than in theory, and you may have had your kinetic friction be a little bit more bumpy like this. So the reason we're taking the mean is to kind of smooth that out right there. So this peak static friction force was this spot right there. Let's just say we measured it to be 7 newtons, and then this mean kinetic friction over here, let's just say we measured it to be 5 newtons. And then you went on and you did some more things like the floor, and maybe you did cardboard or something like that. And we're just checking out different things. And maybe the floor was a little bit stickier, so maybe this went up to 10 newtons. I'm just making up numbers here. Maybe this was 6.5 newtons. And maybe the cardboard was more slippery, so maybe the peak static friction here was 9 newtons and this was 3 newtons or something. So the idea is it's going to depend on the two surfaces, whether it's a wood block against a piece of paper, whether it's a wood block against the floor, whether it's something else. What do I have here? A piece of bubble wrap sliding across is going to be a little bit stickier. A pen sliding somewhere is going to be a little bit smoother, right? So all these things are going to change what your peak static friction force is going to be and what your mean kinetic friction force is going to be. So then we popped down here, and hopefully you had a chance to do this. If not, we can do it in class. We were looking about what is called the coefficient of friction. So in a minute, I'll describe it a little bit more. But it says the friction force is always some fraction of the weight. It's not always, but it's pretty much going to be some fraction of the weight. So I didn't print off the part of the data table that had the weight. So what do I mean? We had our block, and we had this, and we had this. So in the data table up above here, we had the weight of all this together. So I'm just going to estimate right here. Well, I know that this is 1 kilogram, so it has a weight of 10 newtons, or 9.8. And then this is 1 kilogram, so that's 10 newtons, or 9.8. We'll just call it 10. So this is 10 newtons, this is 10 newtons, that's 20 newtons. And this, if I put it on a scale, maybe has a weight of about 3 newtons. So my total weight here, for my previous data table, my total weight, I'm just going to estimate mine as 23 newtons. And what we see is that none of these friction forces ever get to be more than this total weight right here. So what I'm saying here is your peak static friction force is always some fraction of your total weight. Same with your kinetic friction force, it's some fraction. It's never going to be more than this. And if we divide those things, if I take my, say for example, static friction force and divided it by the weight, then we would get what's called the coefficient of friction. So here it says, divide the friction force by the total weight of the block and masses to find the coefficient of friction. So how do I do that? I have table here, and to find my coefficient of static friction, I'm going to take 7 divided by 23. And let's see if I can grab my calculator. So there we go. This calculator is not that great, but you can see this here. So I just do 7 divided by 23, and I get 0.3. And then over here, if I do 5 divided by 23, so my kinetic friction, 5 divided by 23, 5 divided by 23, and I'm going to get 0.22, 0.22. And this is called the coefficient of friction. This is actually a measure of how sticky or slippery it is between the wood block and whatever surface we are on. So between the wood block and the table, my coefficient of static friction is 0.3 and my coefficient of kinetic friction was 0.22. So let's dive into a little bit more about what coefficient of friction means, and we'll get an equation for it. And you can calculate the rest of these coefficients of friction, and all these numbers should be a little bit different. And they should all be a number between 0 and 1. So let me talk a little bit more here about coefficient of friction. So coefficient of friction, once again, it's a measure of how sticky or slippery two surfaces are. How sticky or slippery two surfaces are together. So every two surfaces together are going to have a coefficient of friction. The calculator against the paper, the wood against the calculator, the pen against the paper. And this is not something that you can predict, it's something that you actually have to measure. And that's what we did in this lab, is we technically measured the coefficients of friction of the wood block between different surfaces. By the way, coefficient of friction is kind of a lot to write out, so there's actually a symbol that stands for coefficient of friction. You might want to put C or COF or something like that, but it's actually this Greek letter right here, which is a mu. It's the Greek letter mu, and that stands for coefficient of friction. In fact, there's actually two different coefficients of friction, as we saw over here. There's a static and a kinetic coefficient of friction. So we sometimes will write mu s for the static coefficient of friction, or mu k for the kinetic coefficient of friction. And it's just a number that tells you how sticky and slippery it is between two surfaces. You can imagine things that are really slick are going to have a low coefficient of friction, and things that are really sticky are going to have a high coefficient of friction. Now this excludes things like glue or tape, which literally stick and adhere to something, and you're not going to really get anything sliding there. So this is going to be a measure of two things that could slide. Even if it was really, really sticky, like peanut butter is really sticky, it would really have a high coefficient of friction, but it's not stuck like glue, right? In general, what we see is that the static coefficient of friction is usually bigger than the kinetic coefficient of friction, might be equal to it. How would that look on the graph? Well, if you were doing this lab, and this may have happened for you also in the lab, time on this axis, once again, force on this axis. Maybe you were pulling and you saw this go up, 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 and then it just kind of did this over here. So here's your peak static friction right there, and then here's your kinetic friction. And it is possible to have your static friction and kinetic coefficients of friction be the same. So right there and right there, my static friction force was the same as my kinetic friction force. And that can happen sometimes. But this one is almost never going to be above this one. It would be a pretty weird graph if you were graphing and you were pulling and you were pulling and you were pulling, and if it moved and then the friction force got bigger, then it wouldn't be moving anymore, and that would be kind of a funny thing to do. So that's why this one is almost never bigger than this one. Okay, so how do we use this in like an equation or to do some physics problems? Well, let's draw this scenario here of the wood block, and let's just draw a quick diagram of it, and then we'll draw a free body diagram. So looking at the wood block from the side, there's the block, there's the table, and then here's the little hook, and then there's the force sensor, and you were pulling on the force sensor over there like that. Okay? And this is the situation. We're pulling on this way. Of course, there's gravity and there's a normal force. As always in physics, we like to simplify things. So we're going to translate this into a free body diagram. So the free body diagram, looking once again from the side of the wood block. So we're looking at it from this perspective, and you're pulling on it this way, like side-on perspective, right? So we're going to draw a free body diagram, and that free body diagram is going to be like this. Of course, we're going to have gravity going down, so I'm going to label that as Fg, force of gravity, and we're going to have normal force going up like that. Okay, and those should be balanced. How did I do this time with my arrows? Are those two equal? Maybe didn't do that great of a job. On this side, we're going to have an applied force, F applied, and then going this way, opposing the motion, we're going to have friction, F friction. Now it turns out in all the scenarios in the lab, we had equilibrium. And in one case, we had a static equilibrium. Oops. Static equilibrium. And then in one case, we had a dynamic equilibrium. Now, it's a little unfortunate that we don't use the same words, meaning static matches up with static, and dynamic matches up with kinetic. So why don't they both use dynamic or both use kinetic? I don't know. I always say that physics people like to make things simple. Sometimes that's not totally true. So what can we do here? Well, we can start to figure some things out and calculate some things. For example, I can calculate what the friction force is if I know what the applied force is. And that's really what we did in the lab. And I can also calculate what our normal force is if I know what our gravity force is, right? So let's walk through that a little bit. The way we usually solve physics problems that have things going in multiple dimensions like this, multiple directions, is by breaking things down into an x direction and a y direction. So let's see what's happening in our x direction right here. In our x direction, what we know is that our forces are balanced, meaning our friction force is going to equal our applied force. So we're going to have F friction like this, and that's going to be the same as F applied. I know that because I'm in equilibrium, and when things are in equilibrium, all the forces are balanced out. In the y direction, we also have forces that are balanced out. The normal force is going to be balanced out by gravity. Normal force is going to equal gravity. Now, it turns out that's not always the case. When we tilt things and go onto ramps, when we're going to make things off at an angle, then that's not going to be the case. But as long as we're on a flat surface, then this normal force is going to equal that gravity force. So this actually allows us to really figure out the lab and put these numbers in. What do I mean by that is that we put in the peak static friction force here. How do we know that this was the friction force? Because we weren't measuring friction. We were actually measuring how hard were you pulling with a force sensor, right? So how do we know that that is equal to the friction force? Well, that's just from our free body diagram right here. So whatever applied force we were pulling with actually equals the friction force. And that's what we have over here. In the x direction, the friction force is equaling the applied force, right? And then in the y direction, we have our normal force is going to equal our gravity force. So how do we get coefficient of friction into this mix? Well, what I had said over here in order to do this is I said, divide the friction force by the total weight. That's not actually totally true for what friction is. And let me grab a different piece of paper here and we'll move on, and I want to show you what the real definition for coefficient of friction is. So the real definition for coefficient of friction, if I have mu here, if I want to find out what the definition for coefficient of friction is, it's actually going to be the normal force involved instead of the weight. So we're going to take the friction force divided by the normal force, and that's going to tell us our coefficient of friction. Once again, going back to our data, I had you divide the friction force by the weight, but the real definition is the friction force divided by the normal force. But it's okay in our lab that we did that because what we saw from our free body diagram is that the normal force is actually the same thing as the weight. Remember, the force of gravity is the same thing as weight. Right? That's what force of gravity means as weight. And by the way, we do have a formula for this. Weight is going to be m times g. So we can figure that out. Yep. So down here, if you want to figure out the coefficient of friction, you need to know what the friction force is, and then you need to know what the normal force is, and if you divide those, then you get the coefficient of friction. This is useful sometimes, but in other situations, you're actually given the coefficient of friction, and you want to actually find the friction force. So this equation is actually more commonly written like this, that the friction force, F of friction, is going to equal the coefficient of friction times the normal force. And that's what the friction force is going to be. Now, of course, we have two different friction forces. We have a static friction force and we have a kinetic friction force. Let's just do a quick example. Let's say I've got a box on a table, and let's say I'm given that the coefficient of static friction is 0.3. Okay? And let's also say that I'm given that the mass of this thing is 3 kilograms. And the question is going to be, how much force do I need to get it moving? How much force to get the block moving? Okay, that's going to be the question. 3 kilogram block, and I'm given the static coefficient of friction is 0.3. and how much force to get the block moving. So how can I set this up? Well, most physics problems that we're going to do involving forces, we're going to draw a free body diagram, which is going to be the same as the one I drew before, but we'll draw it again. So there's my block. I'm going to have gravity going down. I'm going to have normal force going up. Those are going to be equal. I'm going to be pulling here my applied force, and I want to know how big my applied force needs to be in order to overcome the friction force. And if the block is just starting to move, then my applied force is going to equal my friction force over here. So really the question is asking, what's my friction force going to be? And in my equation up here, I can say my friction force is going to be my coefficient of friction times my normal force. I'm given the coefficient of friction. If I'm looking for this force of friction, how do I find the normal force? Well, look back over here. In the up and down direction, these two things have to be balanced. So in my y direction, as we had written before, I know that my normal force has to equal my force of gravity. How do I know what my force of gravity is? That's the same thing as the weight, and that's just m times g. I've got 3 kilograms here for my mass, so I can do 3 kilograms, multiply that times g, which is 10. And remember, the units for g are meters per second, so I know that that's 30 newtons. This is going to give me a weight in newtons. Now I know that my normal force is 30 newtons, so let me plug that in there, and then we're basically done. My friction force is going to be 0.3, that's my coefficient of friction, times my normal force, 30 newtons, right? I think that we can do this without a calculator. 3 times 3 is 9, and then we just move the decimals. So 9 newtons. That's the maximum force that static friction is going to be able to push with. So I know if I want to pull this thing, I need to get just barely more than 9 newtons in order to overcome the friction force. So that's just a nice sample problem for how you can work with coefficient of friction, how we can use free body diagrams to help solve physics problems, right? We talked about coefficient of friction and how coefficient of friction works, and we related it to our lab and the blocks and the force sensor pulling. All right, thanks for watching.